Today I'll be talking about what if you take an end-to-end model and actually deploy it in the real world? What happens, all the craziness, how do we actually ship end-to-end? So a little bit about what we focus on at Electric Sheep. In today, we have our built infrastructure, our man-made kind of civilization, and it's actually in this constant kind of balance with nature, which is pure entropy, trying to decay and basically break it down. So what you have is actually this massive industry hiding in plain sight of millions of people going out daily and performing maintenance. This maintenance takes the term of mowing lawn, pest control, road repair, anything that's this constantly dealing with how to maintain nature in our society. Now, this industry is actually really interesting once you get in the weeds of it because there's not enough people to perform all this constant maintenance. So what you have is a lot of shortcuts happening. Some of the most notable ones are people are using unregulated gas equipment. It accounts for 5% of US air pollution. Because you're trying to minimize time on site, you end up using really cancerous herbicides to do weed treatment. And that's poisoning our water tables. It's not great. And then this industry as a whole, because you have dudes operating heavy power equipment on trailers, has one of the highest accident rates according to OSHA of any industry in the US. So at Electric Sheep, we really have this idea of basically swarms of low-cost, sub-3K, animal-like robots that can perform these types of tasks that you might see. So we have a wide variety of robot platforms we're looking at, but the core idea is they should be able to go out, have limited connectivity, be able to operate in places like the Sierras or even an HOA where there's just not guaranteed, maybe at best you have LTE 4G, and be able to perform tasks reliably with minimal instruction. Now, to do this, we do feel in the limit you have to have a single AI foundation model power these types of equipment. And the reason is, once you deploy a robot enough, you realize, okay, the unstructured world is pretty complex. Even mowing a lawn, you might hit a gopher hole, tree roots. It's actually quite complex to just wake up and perform these tasks. And you really want a robot that can go out there and learn and get better over time. So what we've been doing at Sheep and what we're talking about is training a single model that can power different types of equipment. So it can be anything from a simple mower to a robot that can actually operate like a string trimmer or a leaf blower. A lot of what we do is just put power tools on robots, and it's quite fun to see actually. And then talk about how we deploy that, and then how we make it robust over time. So as roboticists, I think we all know what we're trying to get to, which is this general sense of physical intuition of the world. So obviously you can see in any animal or any creature, this generic spatial understanding, this ability to wake up, perform tasks reliably. Now, if you take an ML approach to this, you really are saying, okay, well, it comes down to two things, the right types of data to learn on, and then the right types of model architecture. And that's really what we've been thinking about. Now, I would actually argue that learning physical intuition from just static web data doesn't really make a lot of sense. I think some of the reasons are web-based training is not going to have unique kinematics of a robot. Some robots are two-wheel self-balancing. You're not going to find that kind of interaction data on the web. Also, what you see is most of these VLMs are very large. When you actually want to run a robot on the edge out there with minimal connectivity, you really can't have these massive large web models to be in operation. And finally, there's this no on-policy training. So there's a lack of interaction data, right, which is fundamental. How do you learn from actions if you only have a passive data set? Now, there is a whole nother camp of where we can actually draw our data from. Most of us are familiar with it as roboticists, which is just the general concepts we've actually created over the past 60 years of physical intuition robotics. And what that turns into is collision awareness, local planning, global awareness, SLAM, these sort of topics, right? We can actually use these to generate data for our models as a pre-training step. And the way you can do this is actually, of course, simulation. So here are some examples from NVIDIA's Isaac simulation that we use for pre-training. Here you can have perfect world state. You can have robots roll out, generate policies, learn from experience, and then train these sort of physical intuition models. So what do I mean by that? All right. So the first thing to do is to give our surface coverage, semantic area robots this sort of intuition for the world was we try to train a GPT for outdoor work. So instead of just saying, okay, let's just take in demonstration data and just predict action, it's like, can we learn some of the core concepts of robotics? So what we had was a world model take in ground truth maps, depth, segmentation, and then actually output these same representations. So now you've taken your kind of classic 101 surface coverage, mobile AMR system, but distilled it into a model. What it looks like in the real world is then you can actually take our platforms, roll them out. You have video data come in to a single model. We're not going to get exactly into the architecture yet. It's basically a transformer with some tricks for context windows to how do you do something like SLAM. But then you can predict these like very general systems. So you have like the core kind of foundation model that's predicting your general robotic concepts of SLAM, semantic understanding, obstacle detection. This is all trained in simulation. Now, before I get into how we then can teach to actually perform tasks, I just want to go over some of the really, this is why I'm so into simulation is like the cost to do this is so low. You can train very small models in sim because you have very clean, coherent labels. It's like really well-crafted ground truth, and that allows for fast training times. But also, the generalization you get, I think, is what is most impressive. When you can train something purely in sim and then test in the real world, even if you just test in your office, the fact that it works means it's likely going to work a lot other places because there was no data that you overfit to. So our robots work out of the box on day one. They can go anywhere in the country and operate. And we've done this now on like thousands of properties. We have a very good generalization from synthetic pre-training. That is probably one of the, if you take anything from this talk, definitely check out synthetic data. It's quite powerful. Okay, but given this sort of like world model of like key classic robotic concepts, how do we actually teach an agent to perform tasks? So there's a lot of ways. One that we're pretty interested in is obviously reinforcement learning. It's just simple. You can specify reward functions. You're in sim. You can just roll out and try things. But this isn't the only way. You can actually just use planners and like IO demonstrations. But here what you have is essentially the world model feeds into like a policy embedding head, and then you can train on top of that with your favorite like SAC, PPO, and simulation. Now once you have that, you're at the core problem of like a robotics company, right? So you have your prototype robot, maybe it mows the lawn, maybe it string trims, but now you have to deploy it. So at Electric Sheep, we actually took a pretty unique approach to deployment. What we originally did was actually bought landscaping companies across the country and then turned them into sandboxes for our AI agents. So this allows us to sort of incubate our technology and train it every day in our own operations. So what does that look like? So what you have is a person has robots in the back of their pickup truck. They're hit multiple sites in a day. Each day they put a robot down and have it execute while they perform work and generate revenue. So you can see here as the robots are just placed down. There's no top map. There's no pre-knowledge baked in. The only operation the guy has is an on-off button. And then the policy of the robot is actually rolling out, and it's be able to do these tasks. This is actually, I think, one of the cool things where you see like an end-to-end system like start exceeding in this space is because normally in like mowing robots, you see like a teach and repeat. You have to have a skilled operator. They have to know how the robot would behave. With like this basic raw intelligence, you can now just deploy things with minimal UX. So in our industry with this high labor churn, you don't really have to worry about like the next guy knowing how to use the system. The system is as easy to use as like a leaf blower. It's just point on and shoot. But now, given this, the question is, okay, well, how do you learn from that experience? Because now what you want to do is be able to actually keep shipping these things, have them learn over time, and get better and better. So I'm not going to go into everything, but there's a couple like key ways that you can actually then start providing reward signal once you have like agents like this deployed. So one of the most common ones is like 3D reconstruction. So they can come back, upload a log, you can do bundle adjustment, run cold map in the cloud, and then actually say like, okay, what did you cover the lawn optimally? If not, here's some negative reward. The other thing that's really interesting we're exploring is using VQA. So you can like run it through logs and then actually understand like, well, did the robot do something like break containment? Did it leave the grass? And then provide negative signal that way. And this is, I think one of the core problems of robotics is like, how do you scale robots without scaling engineering? Automated tools and using RL is definitely like one of the most promising directions we have right now. So you can see how that running this data engine in our crews actually led to some improvements. So one of the most notorious challenges with outdoor robots is sun glare. Our robots are expected to work at like 6 a.m. They have to stare right into the like rising sun and operate. By using this RL policy in our internal crews for a while, we've actually been able to like become quite robust to it. And now they can actually look at sun and just drive straight through. And then the other examples are, there was like rare containment situations where it was like, okay, like, you know, I kind of get grass, I get flowers. I've actually never heard of flower deploying these robots. But things like dirt boundaries that are very like wide, it would struggle on. Using this sort of RL feedback, you can now see our world model is able to understand these and get better. The next thing we're exploring, though, and this I feel like is really the true unlock. I don't have much results on it to share, but it's definitely like where we want our products to go, is language-based feedback. So if you can really have a robot like ask someone at the end of the day, how did I do? And they actually give them feedback, and you can turn that into a reward signal, which is not that far away. Like you can run onboard LLMs, and then you can also easily say like, okay, this was like sentiment positive, sentiment negative. So you can definitely get structure back from that. This is going to provide a really natural, like fluid way to actually give this intuition. So where are we at now? Running this data engine, we've been able to actually operate now on over 1,000 properties. So we actually hit a point where these end-to-end agents can actually go out and be highly reliable. And we're now actually ready to start selling externally. So in the winter of 2025, we will be now, like, you can just go to our website with a credit card and buy these machines. So that's gonna be pretty exciting. And then we've also scaled tax diversity. So instead of just looking at mowing at scale, now we're actually in pilot programs with these more like robots that can use different types of power tools. So you can have a string trimmer, a weed sprayer, a leaf blower. And then we're looking at like, how do you scale now in tax diversity with the same foundation model? So that's it. If anyone has any questions, be happy to take them.
Are you putting the actual foundation models on the robots, or are you doing it off the robot?
Yeah, they're on it, because that's like, our models are actually a lot smaller, and I do think a lot of that is because you pre-trained in sim, but they're only like 100 million params at most.
Not doing 7 billion per one day.
No, you can't. I mean, like, I just think that's kind of, for like these types of applications, like, I think it's gonna be very hard to get something that big real time on these systems. Well, so I mean, there's maybe different approaches here, and like, robotics as a whole, it's the high reliability that kills you. I think anyone who's shipped a robot, you know, no one cares about your fancy math or your 70% reliable demo. It's the 99.99%. So all that to say, it's going to be really hard to know how everything plays out until you really have robots working. But one thing that's different about our approach than just training on raw demonstration data is we actually train to learn like key foundation concepts.